Ever pondered about the underlying principles that make your favorite programming language work the way it does? Well, let's dive into the fascinating world of programming language theory, or PLT for short. This is a branch of computer science that zeroes in on the design, implementation, and analysis of the formal languages we know as programming languages. But where did it all begin? Let's rewind to the 1930s. The roots of PLT are intertwined with an abstract mathematical theory known as the lambda calculus. This theory, created by Alonzo Church, was all about functions, variables, and the application of functions to their arguments. It's from this foundational concept that the principles of today's programming languages were born. So, every time you write a line of code, remember, there's a rich history and complex theory making it all possible. The road to our modern programming languages was paved with groundbreaking milestones. Let's embark on a journey back in time, to the days when computer programming was still in its infancy. Our first stop is the 1940s. It was in this decade that the very first programming language, Plankalkul, was conceptualized by Konrad Zuse. Although it was not implemented during his time, it was a significant first step, embodying concepts that would later become fundamental in the field of programming language theory. Fast forward to the 1950s, and we arrive at the birthplace of Fortran. Developed by IBM for scientific and engineering calculations, Fortran, short for Formula Translation, was the first high-level programming language to gain widespread adoption. Its creation marked a significant shift away from machine-specific assembly languages towards a more abstract, human-friendly way of communicating with computers. As we move into the 1960s, we witness the emergence of two more legendary languages, ALGOL 58 and Lisp. ALGOL 58, or Algorithmic Language 1958, was influential for its introduction of code blocks and the begin and end pairs, elements we still see in many contemporary languages. On the other hand, Lisp, standing for list processing, was the first language to focus on processing symbolic data rather than numerical data, pushing the boundaries of what programming could accomplish. These pioneering languages, Plankalkul, Fortran, ALGOL 58 and Lisp, each brought something unique to the table. They challenged the status quo, pushed computational boundaries, and broadened our understanding of what programming languages could do. These languages were not just tools, they were catalysts for change, sparking innovation and laying the foundation for the diverse array of programming languages we see today. These pioneering languages laid the groundwork for the myriad languages we have today. Programming language theory is not just about programming languages. It's a vast domain, stretching its tendrils into numerous subfields. One of these is formal semantics, which helps us understand and predict the behavior of programs. This is complemented by type theory, a branch that scrutinizes data types and their interactions, ensuring that the operations we perform are sound and safe. Then we have program analysis, which is all about examining the programs themselves, identifying potential bugs, and optimizing performance. It's a bit like being a detective in a world of code. In the same vein, comparative programming language analysis helps us understand the strengths and weaknesses of different languages, guiding us in choosing the right tool for the job. Metaprogramming, on the other hand, allows us to write programs that can manipulate other programs, or even themselves. It's like Inception, but for code. And let's not forget about domain-specific languages, which are tailored for specific problems or industries, making them incredibly efficient at what they do. Finally, we come to compiler theory and runtime systems, which are all about translating our high-level code into machine instructions and managing their execution, respectively. All these intricate fields converge to make programming languages the powerful tools they are. The evolution of programming language theory is a testament to human ingenuity. It's a journey that begins with the birth of lambda calculus in the 1930s and continues through the creation of Plankalkul in the 1940s, to the development of Fortran in the 1950s, and the emergence of ALGOL 58 and Lisp in the 1960s. Each innovation has played a crucial role in shaping the world of computer science as we know it today. But the evolution of programming language theory is not just about these monumental landmarks, it's also about the continuous refinement and expansion of the field, which encompasses formal semantics, type theory, program analysis, comparative programming, language analysis, metaprogramming, domain-specific languages, compiler theory, and runtime systems. The importance of this theory cannot be overstated. It gives computer scientists the tools they need to create efficient, robust, and secure software. It's the foundation upon which all other aspects of computer science are built. The dissemination of research in this field is facilitated through academic conferences and journals like POPIL, PLDI, ICFP, UPSLA, and ASPLOS. These platforms allow scientists from around the world to share their findings, discuss new ideas, and contribute to the ongoing evolution of programming language theory. Understanding programming language theory is not just about coding, it's about appreciating the science and art behind it.